Good morning and welcome to the 28th lecture. So in this lecture, we will see some examples from the previous lecture, that is linear block codes. And in the next part, we also see how to correct errors using single errors using Hamming code. So initially, we begin with an example from the linear block code. So we have a scenario here. That is, in this example, it says consider a linear block code with n is given here. That is, the length of the code word is 6, and also the number of data bits k is equal to 3. The check bits of this code are derived using the discrete relations. The relation is given here. It says that you need to have the data bits that are 3 bits in length. You need to design the code words that are 6 bits in length. While designing the code words, you need to add some redundancy bits that are the check bits. Those check bits here are mentioned. How to derive those check bits are given here. That is, for example, C4, which is the first check bit, that is derived by adding the first and second data bit. Similarly, the second check bit, or the fifth bit in the code sequence, is derived by adding all the data bits, because we know that there are 3 data bits. The k value is 3 here. And now, similarly, you need to derive the value of the last code bit, or the third parity bit, or the check bit, third check bit, that is D2 and D3. They are XORed. First, we need to find the generator matrix G. So to find the generator matrix G, uh, we need to know P, the parity matrix. So there is no mentioning of the parity matrix here. But using the idea of these check bits, we can find out the parity matrix, because each column will be these items here. Okay, with the help of parity matrix, we can find the generator matrix. That is nothing but I and P, identity matrix and parity matrix combined together. And then we also need to find the code words of the linear block code. We need to find all the code words. So here, given that n is equal to 6 and data bits are 3, so with the help of 3 data bits, how many n's we can generate? Because when we have just 3 data bits, the combination may vary from 000, 001, and up to 111. So all these data bits, what are the different possible code words that we can have, that we need to find out here. And then the next question is, find the error detecting and error correcting capabilities of the code. So how can we determine the error, whether there is an error in the received sequence or not, and how can we correct it? I mean, how many bits can be corrected? So that is based on the Hamming distance. And then we also need to find H and H transpose. That's a parity check matrix and its transpose. Okay, let us see how to find out these parameters one by one. So with the help of this, we need to find out first the parity matrix. So from the given data, we know how to find out C5, C6, and C4, 5, and 6. We can write the parity matrix P. So let us write that. How do we write that? C4 is equal to D1 XOR with D2. So that first 2 bits we need to XOR, and we get C4. And for C5, we XOR D1, D2, and D3 and get C5 here. And C6, we XOR D2 and D3 and we write that here. So this, I have written here that this is a column wise. So the parity matrix here, for the first column is generated from this. So I have indicated the red color here. The second column is generated by this, by XORing D1, D2 and D3, and C6 is generated by here. From this it is generated here. Okay, then the generator matrix G is very simple. G is nothing but the identity matrix and the parity matrix. So identity matrix, very simple. That is a 3 cross 3 matrix where along the diagonal you have ones and all other elements are zeros. And next we have the parity matrix. We have generated the parity matrix here, so we will be adding that here. I mean combining with I here. So I is a 3 cross 3 matrix and the remaining elements are the elements from the parity matrix P. Alright, next as we know G, can we find out the code word? Yes, we will try that. C is equal to D and G. This is a well-known relation. So now data, how to find out the data? What we have assumed data as 001, because we know that the value of k is equal to 3, right? So if we have the value of k is equal to 3, then we can have data starting from 000 and or 001. Similarly, we can have many, 2 power k minus 1 combinations, or the finally we have 1, 1 and 1. So with the k bits, we can have 2 power k minus 1 combinations, that is from 0 to all ones. So we need to pick any one of these data. Maybe in this case or in the previous case we have considered 001. So with this 001 data, we consider D as 001 and generator matrix G we have already computed. With the help of that, we can find out the code word C. C is equal to D multiply G. That is what shown here. You have the data and the generator matrix is already determined. We just need to multiply. That is this D multiplied by the first column here. So we should be getting then the value of C1. For example, 0 multiply 1, 0 multiply 0, and 1 multiply 0. It's a 0. So C1 should be 0. Next C2, how to find out C2? C2 is D multiplied by the second column here. So that is again when you multiply 0 and 1 and 1 and 0, it becomes again 0. And similarly, the remaining bits we can find by multiplying this data with the different columns here. So if you notice that C6 will be 1. Yes, C6 is 1, but C1 and C2 are 0. That's what we have determined in this multiplication right now. Yes, in this way we find that the bits of the code sequence or code word for this particular data. But we can have many data sequences, for example, varying from all these data sequences we may have. For those data sequences, we get different code words. But in this case, we have just considered one. We can extend that. We can compute the same for different different data bit sequences, and we can determine what are the different code words we would generate. So yeah, this is the code word that we have determined for one particular data set. In the same way, yes, we can find the code words for different other data sequences also, as I mentioned, 000, 001, up to 111. So many data sequences we can have with the 3 bits, because k value is 3 in the question. And then accordingly we can find the different code words using the same generator matrix. So that would appear something like this. We have different data bit here, and when we multiply data with the generator matrix, we get different code words. What we have found here is 001. That's one data we considered from this list, and then we generated this particular code word 001011, 001011. Yes, and similarly we can find other code words. And here you see another column that is called the Hamming weight. What is Hamming weight? Can you imagine what's Hamming weight by seeing these values here? Yes, the Hamming weight is nothing but a number of non-zero elements in a code word. For instance, here, if you see the Hamming weight column here, it says the Hamming weight value is 3 for this particular code word. So the definition of Hamming weight is number of non-zero elements. So in this code word, how many non-zero? That means ones are there. There are 3 ones, right? So the value here is 3. In this code word sequence, how many ones exist? There's 4, right? So we have the Hamming weight as 4. Similarly, you can check other values. The Hamming weight, for example, here in this case is 3. That is here 3. So in this way, we find the Hamming weight for different code words. So what is this Hamming weight indicates? That should be indicating something related to error check or error correction capabilities. Because in the question we also need to find out the error check or error correction capabilities. Let D minimum, from the table we observe that D minimum, the minimum Hamming weight is 3, right? The values were in the last column were 3 and 4. So the minimum value is 3. Minimum Hamming weight is 3. So here now, the maximum number of errors that can be detected. How many errors we can detect? How many errors the receiver can detect? That is decided by this value, D minimum minus 1. So this is a generalized equation. How many errors can be detected at the maximum at the receiver? That is D minimum minus 1. That's equal to 2. And the maximum number of errors that can be corrected. How many errors the receiver can correct? That's again decided by this value of D minimum. So it's D minimum minus 1 by 2. So many, uh, you get a value here, so many bit errors can be corrected at the maximum. If the value exceeds above that, then it cannot be corrected. So this is the idea of error detection and correction. So, and also this is the limitation that puts on the receiver when it detects or corrects the errors. Yes, now, so D minimum minus 1 by 2 becomes 3 minus 1 by 2, that is 1. That is single bit correction. To do the single bit correction, the minimum value of D minimum should be 3. Okay, so here we have a note. A linear block code with the minimum distance D minimum can correct up to D minimum minus 1 by 2. So how many errors it can correct? The word here is correct. That is D minimum 1 by 2. So if it wants to correct 1 bit error, then D minimum, the minimum value should be equal to 3. How many errors it can detect? That is D minimum minus 1. It can detect 2 errors, but it can correct only bit error if the value is D minimum is equal to 3. Similarly, you can find for other values of D minimum. Alright, then we need to find out H and H transpose. So here H value is, we know the general equation, H is equal to P and I concatenated here. So P value we have already found. with an I value, we can easily write. With the help of that, we can write here H is equal to P transpose and I. So this part comes from here, and In minus K that comes here. And then we need to find H transpose. So H transpose means you need to convert the rows into columns, transpose of a matrix. So that's very easy. Easily we can find out H transpose. So these are the questions we need to solve, that we have solved. Yeah, so P transpose and In minus K part. And also we can verify that H transpose, because we know a generalized equation that G into H transpose should be equal to 0, or C multiply H transpose is also equal to 0. So we will verify that because we already found what's the value of G, and we got H transpose here. Whether it follows that relation, we will see that. So G is given here, H transpose from the previous slide, we were told to find out H transpose. So H transpose value is here. So when we multiply these, we should be getting 0. So we can easily find out that this value becomes 0. So this can be easily verified as 0. So this is just a verification of H transpose, whether the H transpose value, uh, when we multiply it with G, whether it becomes 0 or not. Yes, this is how we find the different parameters that were asked in the question. Now let us move on to the key topic here, that is single error correcting Hamming code. So earlier we saw that in the linear block code, the minimum distance d minimum can correct up to d minimum 1 by n2. So many errors can be corrected. So that means for a single bit error correction, if the receiver just want to correct one error, the distance d minimum must be equal to 3. Also, from the example, we notice the following: what each row of H transpose has n minus k entries. Yes, this is from the structure of H transpose itself we can find it, because H transpose consists of P and I. So we have so many n minus k number of rows. In the previous example, n was 6, k was 3. So that is 3 number of rows in H transpose. They were of either 0 or 1. Of course, we have values either 0 or 1. So each row had so many entries. That means 3 entries in every row. Those values were either 0 or 1. And we can have 2 power n minus k rows. So 2 power n minus k in the previous example was 2 power 3 rows. So there were about 8 rows, each row having 3 columns or entries. So out of which we can select 2 power n minus k minus 1 distinct rows of H transpose. So it has 2 power n minus k different rows. From that we can choose 2 power n minus k minus 1 different rows of H transpose, because one of the rows will have zeros, all are zeros. So if all entries in H transpose are zeros, then when we find the syndrome vector at the receiver, means there is no error. That corresponds to an entry or corresponds to a code word with no errors. If there is any error when we find a syndrome vector, that will represent one of the rows in H transpose. This is what we have seen in the earlier example in the previous lecture. So if there is the bit pattern is 0, 0, 1 in the syndrome vector, we will check the H transpose, which row of the uh, H transpose has 001. So that particular, for example, if it is in the third row, then the third bit in the code word has some issue, that is error. So in this way, we map from the syndrome vector to H transpose. Similarly, we do not consider, for the same reason, we do not consider a row of zeros, 000, in the H transpose. We do not consider, because that means there is no error. But we consider all other rows, because we are mainly concentrating on how to identify the errors and correct the errors. So we want to those elements where there are errors. So that's why we leave the first, I mean, one of the rows that has all zeros. That means in general, we consider only 2 power n minus k minus 1 rows of H transpose. Okay, the matrix H transpose has n rows, all of them to be distinct, because syndrome shall match any one row. Because if the syndrome value is 001, we will check the different rows of H transpose, which row has the 001 pattern. If two rows have the same 001 or 001, then the receiver cannot identify where the error was. We cannot uniquely identify the error. That's why each row of H transpose should be unique, so that we can map between syndrome vector and any row of H transpose. So based on that, we can decide where the error is. Suppose ith row, the general statement I had mentioned in the previous lecture, if the ith row of H transpose, for instance, we find at the receiver, we find the syndrome vector. And then if the syndrome vector is not zeros, maybe something like 010, this is an example, then we will see the HT matrix, because it has many entries, maybe 111, 000, 001, and so on. Any other entries as here, or maybe somewhere 010. Okay, so now here the syndrome vector is 010. We check H transpose here. Is there any 010? Of course, there should be somewhere that is 010. That is in the fourth row of H transpose has a 010. That means in the received code word, because when the receiver receives a code word, that C will be a combination of, actually C, what is received at the receiver, is actually consists of the code word added with the error from the channel. This is what we represent it as R. Okay, so it indicates that, in this case, it indicates that the fourth bit in the received vector has some error. For example, received bit may be 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, and so on. This is just an example. So when this received vector is seen, and if the syndrome is 0, 1, 0, we will try to map between syndrome and H transpose. It's a mapping process. So then we notice that the fourth row of HT is similar to the syndrome. That means the fourth item, fourth bit here has error. oh sorry, this is the fourth bit, this is the fourth bit. So the fourth bit, 1 2 3 and 4, this is the fourth bit in the received sequence. This has an error, so this is 1, though this should be 0. This is how the error is corrected. So in the previous slide I mentioned that we don't consider the zeros, because if it is 0 means there is no error when we map to S. Okay, so we have some general properties here. So it says here 2 power n minus k minus 1, that is greater than or equal to n. So this is puts a limitation on the code word size, how big our code word can be. The code word should be less than or equal to 2 power n minus k minus 1. So you can check with the previous example. So in the previous example, n was 3, n was 6, k was 3. So that is 2 power 3 minus 1, that is 7. The code word size was 6. So we follow this relation here. And the number of parity bits in n minus k code should satisfy this inequality. That is, n minus k must be greater than or equal to log of n plus 1. So n was 6, 6 plus 1 is 7, log 7, the base is 2 here, and n minus k is 3. 3 is greater than or equal to log 7, right? Yes, this is more than 3, more than 3. So, so this is less than 3, less than 3. So this is 3, because log 8 is 3. This is log 7, so it is less than 3. So n minus k is 3. So again, we need to follow this relation, and in the previous example also it was satisfied. So now we have another important relation to be followed here from this discussion. So the message block size k, we can determine the minimum size of n, the code word, using this relationship. So the code word size must be greater than or equal to the number of data bits used, log of n plus 1. So here n is an integer. So n should be an integer. For example, if you get 4.5, then it should be made as 5 based on this relation. So these are the general relations that we observe in a linear block code. And we can also use this in some of the designs. We have an example here that indicates how to use those relations in here. For example, design a linear block code with a minimum distance of 3 and a message block size of 8 bits. So we need to design a linear block code. To design that, the previously discussed the general relationships, such as the size of the code word, when we know the number of bits to be used, will help us. Okay, so here our task is to design a linear block code, and also it's given that a minimum distance of 3, d minimum is given as 3. So if we know this, we can also determine how many errors can be corrected. And the message block size of 8 bits. So the block size of data is given as 8 bits. That is, k is 8 and d minimum is 3. These are the parameters mentioned in the question. Then we need to design a linear block code. So how to do this? First, if we know k, we can determine the value of n. How many bits we can have in a code word? What is the maximum size of the code word? N. That is given by k plus log of n plus 1. So if k value is 8, then how can we determine the value of n? The smallest value of n will be equal to 12. Yes. Next we have you can get more specification. That is, actually we need to build a linear block code of n comma k. N is 12 here, and k is 8 here. And then we find H transpose. So regarding H transpose, we know certain structure of H transpose. So transpose of a parity check matrix H, that is basically H transpose, will have a size of n here and n minus k. So basically H transpose dimension of this matrix is n cross n minus k. And also we know what are the elements of H transpose. H transpose will have certain parity matrix and also the identity matrix. So its dimension is 12 cross 4. That means 12 rows and 4 columns. Okay. In that case, the last 4 rows here, the last 4 rows will be identity matrix. So it has 12 rows here altogether, but last 4 rows will be the identity matrix. Yes, and then so we get an idea how to write this matrix. Okay, now the first 8 rows are arbitrarily chosen. So we need to write these 8 rows and 4 column structure P matrix that is arbitrarily chosen. But there should be some precaution we need to take. That is, we can write these values arbitrarily, but we need to take care that no row is identically 0 and all rows are distinct. Every row should be different from the previous one. And one choice for HT is here. Here, from this structure of H transpose, we have the parity matrix and identity matrix here, and its total dimension is 12 cross 4, that is n cross n minus k. So here we have these identity elements, which is 4 rows. So only the diagonal elements will have 1. This is the identity matrix. And this is the parity matrix. We don't know how to write the parity matrix. We can write since we know the structure of parity matrix, that is, it has 8 rows and 4 columns, we can keep filling the zeros and ones into this structure. But we need to be careful that these rows are identical and there are no rows with all zeros here. No row is identically zeros. No row is identical, and also we do not require all zeros because we are not uh, interested in seeing all zeros. That means no errors. No, we are not interested in checking that, because if the syndrome vector is 0, it indicates that there is no error. If the syndrome vector is not 0, then we need to check this table to check where is the error, because ith bit in the syndrome vector which is having error is indicated by the ith row in this H transpose. Okay, so all rows are distinct here. So you see here the number of ones are filled here in such a way that there are no 2 rows having same pattern. Okay, this is how we design H transpose. And then we can we can write the generator matrix as I and P. So I, this is the identity matrix, this part, and then the parity matrix is here. Okay, so and then we will move on to the decoding process at the receiver. Now the receiver forms the syndrome S. We know how to determine syndrome S. S is equal to R into H transpose, and accepts the received code if S is equal to 0. So when the receiver receives this R is the received data, which consists of a code word as well as the noise. It will multiply that with H transpose. The receiver will multiply the H transpose and find the syndrome vector. If the syndrome vector value is 0, that means that code word is perfect, there is no error. Otherwise, it has to check the H transpose and find out where the error is. Okay, so now the receiver decodes as R is equal to CI. It considers that code word. If the minimum distance is valid, that is, it's also a valid code word. See, you have so many code words possible. C1, C2, because we have k number of bits, data bits. So with that we can have so many code words, 2 power k number of code words we can have. Next, single errors are always corrected in that case, but double errors can be detected. If there are two errors, then it can be detected because number of errors we can detect is d minimum minus 1. To detect the, so to correct the single errors, the d minimum value should be 3. 3 minus 1 by 2, that is 1. Okay, so in that case, double errors can be detected. But more than two errors, what happens? Multiple errors will usually result in incorrect decoding. The decoding will not be proper. If there are two errors, then those errors cannot be corrected, but just can be detected. Okay, so far what we have seen is the decoding operation. So in this decoding operation, we will receive some data, that is R, and we will compare that R with the original code word C, whether it is the same or not, using the syndrome vector. And the procedure would involve storing or generating 2 power k code words and comparing with R these 2 power k code words. So we need to compare the code word with the R received vector. So there are 2 power k code words possible since we have k number of data bits. So this is basically a lengthy operation. We need to store the data and we need to compare so many times. So the complexity of this operation is n to power k. Because each code word is of length n, the storage required at the decoder would be equal to n 2 power k, because n number of bits in every code word, there are 2 power k number of code words. So altogether, so many bits, n multiplied by 2 power k bits of storage required. So as the value of n and k increases, this becomes too complicated operation. So in order to handle this in an efficient way, the current decoding operation is more complicated in terms of storage as well as number of comparisons required. So how many comparisons and storage required, that is mentioned here as well as here. So yeah, this is more complicated because we need to do more comparisons and we need to have more storage space. That is all difficult. So in order to address this, we follow another method that is called as table lookup decoding using standard array. We divide this. We will see how to do that to simplify the process. Suppose that n comma k linear code word is used for error correcting purpose, and the different code words we can have are c1, c2 up to c power 2 power k number of code words. For example, when the value of k is equal to 3, we can have 2 power 3, that is 8 number of code words we can have, because the data can take different values. Data values can be, if we have just 3 bits, how many data sequences we can have? 000, 001, 101 up to 111. So all these we can have a code word. So we have C1, C2 up to C2k number of code words, a code vector we can have. All right, then let R be the received vector at the receiver. So R can be any one of 2 power n tuples. N tuples represents n number of bits. And the decoder has a task of associating R with one of the 2 power k n tuples, n number of bits, that are valid code words. So when we receive R, we need to compare this with how many? There can be 2 power n. Associating in the sense you have to compare with, match with 2 power k valid code words. Okay, because why do we have 2 power n here? Because the code word size is n bits. So code word size, if it is n bits, we can have 2 power n such code words. But we have not transmitted 2 power n code words. We have only 2 power k code words. Those are the valid code words, right? So we need to have a mapping, or we need to have a search out of 2 power n code words, which are the 2 power k code words that we are actually valid. So what I'm saying here is, for instance, n is equal to 6 in the previous case. So when n is equal to 6, we can have code words in the sense C1, C2 up to C6. So these bits can be 0 or 1 in any value. So we can have 2 power 6 code words. In reality, we can have 6 code words, but we have not transmitted 2 power 6 code words. We have transmitted only any of the 2 power k code words, because 2 power k code words are legal code words, because our message bits are only 3, k is equal to 3. Maybe message bits are 000 to 111, these combinations, that is 2 power k combinations. So for these message bits, we have generated different code words, C1 up to C6, right? C6, but not for all these. So we have only 2 power k valid code words, which are n bits. But actually, we can have 2 power n code words. Maybe due to some error, it has become any of these values. They are also n bits. N tuples indicates n bits. Okay, so we need to perform, receiver has to perform this matching to identify what is the right one. Okay, now the decoder can perform this task instead of comparing and checking all the, it can do this task by partitioning the 2 power n into 2 power k disjoint sets. Instead, in this 2 power n, actually 2 power n code words we can have, but these so many code words are divided into sets of 2 power k different sets. Those sets are defined as T1, T2 up to 2 power tk, such that each subset contains only one code vector Ci. So Ti has one code word, T2 has another code word, and so on to Tk code words. We can 2 power k code words we can have. They are partitioned. Now it's very easy. You just need to check if the received vector, received data at the receiver, whether it belongs to Ti, whether it is any of the code words, then decoder identifies Ci as a transmitted code vector. Yes. Next, correct decoding result if Ci, the code word plus error pattern, belongs to Ti. This is what the actual operation takes place at the receiver. In the previous lecture, we have seen this, how the receiver will correct. Basically, receiver will add the error pattern with the received code word and checks whether it matches or not. So that is the general step as mentioned here. Or incorrect code word decoding if Ci plus E is not belong to Ti. Okay, we will see a simple case here. The code word vectors C1, C2, 2 power k code words are placed in the first row. How to write it? In the first row, for example, C1, C2, C3 and C2k, so many code words we write in the first row. We also take care that all the zeros will appear first here, those code words. And then we go for writing the second row. How to write second row? We write here E2, and then here we add E2 and C2. here E2 and C3 and so on. Just basically the second row consists of adding E2 to all these elements here of the first row. So the second row we need to find out E2, that is any one of 2 power n minus 2 power k tuples appearing in the first row, not appearing in the first row. So first row has C1 to C2k number of code words. Now we need to determine E2. E2 is a code word which is not appearing here. That is, we have only 2 power n minus 2k combinations. I mean, so many entries. We have any one from this. And next we need to find out E3. E3 is again a code word which is not appearing here. An unused n tuple E3 is chosen to begin the third row. So which is not used here is chosen here because we have so many code words 2 power n and 2 power k. So we need to choose one from that here. Similarly, E4 is also again another code word which is not used anywhere here, and so on. We go up to 2 power n minus k. So this is how we write the table here or the code vector here. So okay, so this is the end of today's lecture. So this method indicates how by partitioning the code words, the receiver can simplify its operations. So here basically the number of comparisons or the storage size has reduced compared to the previous method where we use the syndrome vector storing and comparing, etc. So this is a benefit computationally, it is much more beneficial than storage and computation. Okay, this is the end of today's lecture.